Hello everybody, it is nice to see you again in the Kinematics and Dynamics of Machinery class. In the previous segment, we discussed the velocity analysis by instant-centered method. Now, we will discuss another method in analyzing the velocity of the mechanism, that is by the Polygon method. In the Polygon method, you will use a lot of vector polygon in the analysis. Before I introduce the fundamental concept of the Polygon method, I want to review a little bit about linear and angular velocity. If a link, as you can see in the slide, in the pure rotation, we can draw the vector r, which is from the center of the rotation to the point P. Since the link is in the rotation, the derivative of the vector r respect to the time is the velocity. And the velocity vector is always perpendicular to the vector r. So this is the vector of the v. Then angular velocity is the derivative of angular position respect to the time. So this is the fundamental concept of the velocity analysis by the Polygon method. The first one is the rigid body cannot elongate or contract. And the second fundamental concept is the mating surface cannot penetrate or detach. What does it mean? To answer the question, let's see this movie.
In order to execute proper design of a mechanism, velocity analysis is of utmost importance. A designer's real interest is variation of outlet link velocity for a specified inlet velocity. The interesting thing about velocity analysis is, you can determine velocity of any link just by understanding two simple concepts. First concept. A rigid body cannot elongate or contract in any direction. That means, if you take 2 points in a rigid body, it can have two different velocities. But velocity components parallel to the line connecting the points should be equal. If component velocity of point B is greater than A, then link will start elongating. If the case is opposite, link will start contracting. Both these cases are impossible, since this is a rigid body. So velocity components of both points should be equal. This means, if we subtract velocity of A from velocity of B, the relative velocity vector will have no component parallel to the connecting line. It will get cancelled. So relative velocity vector will be perpendicular to the connecting line. In short, concept 1 can be simplified as relative velocity between any 2 points in a rigid body should be perpendicular to the line connecting them. Second concept is applicable to mating surfaces. Mating pair of surface will never penetrate. This is the common mating point, or mating line for both the links. This line represents common normal. The same point can have different velocity on different links. No penetration means velocity component of both the link velocities along common normal should be equal. If velocity component of 2 is less than velocity component of 1, then surfaces will penetrate. If opposite is the case, surfaces will detach. Both these cases are not possible for mating surfaces. So velocity components along common normal should be equal. Since velocity components are equal, if we take a vector difference of v1 and v2, it should have no component along the common normal. So the relative velocity should be perpendicular to common normal. Now we will apply these two concepts on different mechanisms to do velocity analysis of them. First is a 4-bar linkage. We know input angular velocity, and we want to find out outlet velocity. Here approach is simple, we will say that bar at middle cannot expand or contract. Since we know angular velocity of this link, we can easily find out magnitude and direction of velocity of point 1. But for point 2, we know only the direction of velocity. Here, first concept we learned comes for help. Since this bar cannot elongate or contract, relative velocity between these points should be perpendicular to this link, which will lead to magnitude of velocity at point 2. From here, angular velocity of link can easily be deduced. Now consider this mechanism. We know angular velocity of this cam. We want to find out angular velocity of the second cam. This is the common normal at the time of mating. Consider the mating point, which lies on both the cams. We know velocity, direction, and magnitude of this point on first cam. But for second cam, we know only direction. Here, second concept we learned comes to help. Since the links cannot penetrate, relative velocity should be perpendicular to common normal. So we can find out magnitude of v2, which will lead to link angular velocity. Using same methodology, you can do velocity analysis of any other mechanism. Hope you got a good introduction to velocity analysis. Thank you.
So, do you get the idea of those two fundamental concepts? I will conclude two important remarks at here. The first one is about the rigid body. We have the rigid body AB with the joint at its end. At the joint A, we have the velocity VA, and at the joint B also has the velocity VB. Because of different velocity at the joint A and joint B, it means that there is the relative velocity VBA. The direction of the relative velocity VBA is always perpendicular to the line AB because of the first fundamental concept. The second concept is about the mating surface. The mating point is indicated by the point B. Here is the common tangent line. In the mating surface, we have VB1 for link number 1 and VB2 for the link number 2. Because they cannot penetrate and detect, the relative velocity VB2B1 should be in the direction parallel to their common tangent. We will use these two concepts in the velocity analysis by the Polygon Method. After understanding the concept of the Polygon Method in this segment, we will discuss the velocity analysis in the 4-bar mechanism. So, thank you and see you again in the next segment.